And we're back. Welcome back from the weekend and happy Tuesday. Today we're going to continue on with our module on synchronization. But before we begin, a few administrative bits. The reading, a new one has been added. Please make sure you're keeping up with the reading. By the 5th of November, please make sure you're going through sections 6.1 through 6.8, which is pages 257 through 284. Also, Project 2 on threading in C using the C interface, POSIX threads, is due this Wednesday, tomorrow, the 28th of October at the usual 11:59:59 seconds. That's 1 second before midnight. When we last left off, we talked about this idea of the orderly execution of threads within a critical section. We talked about synchronization. And for the synchronization, we said Peterson's solution had to satisfy the three properties for the critical section problem or synchronization: mutual exclusion, progress, and bounded weight. And we saw that Peterson's solution satisfied all of these solutions to the critical section problem. And so let's continue on with synchronization hardware. And so many systems give support for synchronization and this implementation of this access, requesting of access to a critical section. And these approaches or solutions are based on the idea of locking. A lock is a device or mechanism. You request access, and either you get access or you do not. And with this lock, only one thread or process at a time can enter the critical section. Now, in single processor systems, you could implement something like this by disabling the interrupts, and that would mean the currently running code would execute and could not be preempted because the interrupt mechanism is what's used to preempt an executing process. But that's very inefficient on multiprocessor systems, and operating systems that use this aren't very scalable for this reason. And so modern machines implement synchronization using special hardware that forces the system to be atomic, meaning it does not interrupt the execution of certain commands. And in doing so, these atomic hardware allow you to either test memory and set its value, or swap the contents of two different memory words. Now, memory, I say a word and not an arbitrary data structure, a register value. A word is the size of your architecture, 64-bit. If you have 64-bit architecture, a word size is 64 bits long. Okay. And so I looked up, and this is in the x86 Intel hardware documentation, and there's a prefix that you use with certain instructions called operation codes or opcodes. And when you modify a particular operation or command for your CPU in its native language, in the assembly language code, it performs that operation in an atomic fashion, meaning it cannot be interrupted. So it's allowed to proceed without interruption. And so here, let me set the pen, and I'll draw your attention to some of these operations. And so the add operation, if it involves a memory location, a memory operand pertaining to a word, the bitwise compare and exchange is another one. Decrement, increment, the not operator, the or, logical or, exclusive or, and so forth. And so if you specify lock with add or any of these other instructions, a piece of your hardware is engaged and your system will not allow this operation to be interrupted or preempted. It's allowed to execute to its completion. And so in the early days, when I was first learning this stuff, you would look up the atomic instructions in the assembly language for your particular processor for the system of interest, and you would use inline assembly in C code. And this is an example of inline assembly. We have two integers called source and destination. Source gets a value of 1, destination gets a value of 0. And in this command, you say ASM for assembly, open, close paren, and it's delimited by a semicolon. And then on each line, you have your assembly language instructions, and you'd have to look this up and understand enough about assembly language for your particular processor. But in this case, you're going to move values between the source and destination. Here are the variables, and these are the symbols. So you're doing it indirectly in memory. That you're going to add 5 to one of them, and then you're going to deposit your answers into an assignment. And so this is what inline assembly looks like, and this is how in C code you would include assembly language, and it requires you to know the actual assembly language for the chipset that you have for your system's architecture. And then you can take this inline assembly in C and then wrap that in C code and then actually call it as a function. And that's in the old days how you would implement the atomics for your test and set to acquire a lock when you're implementing the entry section and the exit section to protect or serialize access between threads and processes for execution within the critical section. But these days, it's a much kinder, gentler C language than way back when I was an undergrad. And these days, you have libraries to do this. And so for the critical section problem, when you're using locks as opposed to Peterson's solution, your entry section is what you use to acquire a lock. So you can have a function to acquire a lock or a block of code. And then you're going to have the exit section, what we call the exit section for the producer, consumer, and Peterson solution to release the lock. And so the acquisition, acquire lock, that's in trying to use the lock or obtain the lock to grant you access to the critical section, and then the exit is the release of the lock. And then, of course, you have the critical section between the lock acquisition and release, and then you have the remainder section following the release of the lock. Okay, so the two routines of interest, test and set instruction, and this is its definition for what it does. It's called test and set, and this entire test and set is executed atomically. And that means that this entire block will proceed regardless of where execution is. If there should be an interrupt, it will not be interrupted. And the process that executes this test and set, the test and set will not be preempted. So it must complete. It is an atomic unit, meaning the simplest, most fundamental unit. It cannot be subdivided. And so what test and set does, it comes in and you give it a pointer to some word or value, and it returns back the value so that you can test it, but it also sets that value to true. So this is executed atomically. It returns the original value, and it also at the same time sets the value of the register or word passed in as a parameter, as a pointer. It sets it to true. Okay, so this is some pages from C, and it was since C11 version of C that these routines were added, these atomic routines, to the API interface for C. And these are found in header standard atomic.h. Way back when I first learned C, these did not exist, and you had to use inline assembly to construct your atomic test and set yourself. And so these are some of the reference pages. And of course, this reference page tells you what it does. And here is an example using the test and set. So let's assume you have a shared Boolean variable called lock, and it's shared between the two processes that need to synchronize access to a critical section or threads, and it's initialized to false. And so here now, in our while loop, we have a test and set lock. So we have our lock variable, and you test and set it. So this will always be an atomic instruction. And so once that's done, the value returned by test and set, that's what is used to key in for the condition for this while loop. And so if the previous value was 0 or false, well, what happens? You return back the value, and the lock is not locked, but then the action, once you return back the value false, is to set it so it's now true. So at this point, the first thread or process that comes in executes this test and set lock. Only one of them will acquire the lock. The second one that comes in, when it returns the value of lock once it's been updated or lock equals true from the first time that test and set lock was executed, well, the second thread that enters or tries to acquire the lock for this while loop, that block of code for the while loop, it's going to see that the value is true and set it again to true. So it's going to say in this while loop, and its execution for the second thread will not proceed past this acquire lock section. So then the first thread executes its critical section, and then it sets the lock to false. Lock is now set to false. And then once lock is false, the second thread can now acquire that lock. It's going to set it to true. The old value is false after the first thread is set to false. And now the second thread can execute in that critical section. And so it's this atomic test and set that makes the difference because it's not preemptible. It's atomic instruction. Only one of the two threads in its execution will get past this lock barrier at a time. And therefore, only one thread at a time will execute in the critical section. Okay, the other command is compare and swap. And compare and swap, it takes a value, again, an integer. In the first case, it was Boolean, and this value is an integer pointer. So we're going to reference some word, some integer variable in memory somewhere. And it's going to also input an expected value, what you're trying to test against for the current value of this variable, the pointer that's passed in, and a new value. And so what it does is, okay, well, first we save off the current value, and then we test that current value against what we're expecting to see. Is it equal to expected? And if it is equal to expected, then we set it to the new value and return back what the old value was. If it isn't equal to expected, well, we don't do anything. We just return back whatever the current value is. So this compare and swap is also executed atomically. As such, it is not preempted, so it's allowed to run to its completion, return its return value. And so any process or thread that's executing compare and swap is going to allow to do so in its entirety and not be preempted. Okay, so in C11, the same library was added for the compare and swap. And it's called compare and exchange. There's different versions, and you can look at the user guide documentation for it does. But since it's a kinder, gentler C language, they've added this facility because it's so immensely useful and so many people did it. And so you no longer have to implement your own inline assembly, but it's a great exercise to do if you really want to understand the underlying parts of the system. Okay, so there's the other page. And again, in these notes, it explains very nicely in C code what the impact is of executing the compare and exchange. And so here's the solution for locking using the compare and swap or compare and exchange. And again, here in this block up above, that's going to be the entry section or the lock. We're going to acquire the lock. And then down below, we're going to have the release of the lock. And so now you can imagine we have some shared variable, integer lock in memory, and it's initialized to 0. And so the first thing we do is we compare it to 0, and the new value is going to be 1. So now that lock is locked. So when lock equals 0, it means no one has obtained the lock. And when lock equals 1, it means somebody has obtained the lock. And so now the first thread that goes through, it's able to execute this, and this execution goes past this lock section, and it proceeds down to the critical section. So now thread 2 comes along, lock is equal to 1, it calls compare and swap, it is not preempted, and because this compare and swap is atomic, and the second thread, well, at that point, lock is equal to 1. And so we said the semantics of compare and swap, if the expected value is not 0, then it returns back the current value, which is 1. And so while 1 not equal to 0 is true, and that second thread, its execution stays in this while loop and cannot proceed past this lock block of instructions. And so that second thread execution doesn't get to enter the critical section. First thread is done, it sets lock equal to 0, and now the second thread, when it does that compare, it does the swap of 1 and returns back 0, the old value, and it proceeds into the critical section. And so again, we have serialized execution of the critical section using this other atomic instruction, the compare and swap. Okay, and so here is a bounded wait using mutual exclusion with the test and set. And we said part of successful solutions for the critical section problem have a bounded wait and mutual exclusion. Mutual exclusion being the one at a time execution of a critical section between multiple threads, and the bounded wait that no thread will wait longer than a fixed upper bound amount of time. And so we start out and we have waiting equals true. Waiting means that you are trying to access or request access to the critical section. You're going to be waiting for the ICE process. And then T is going to be what we're going to use to hold the status of the lock. And lock is a shared variable, and access to that shared variable is going to be done through the atomic test and set instruction. And so we start out, process I decides it's waiting, and key is already set to true. Okay, so now while waiting starts, and it in that loop does the test and set. And so that test and set is atomic. It returns back the status of the lock, and it sets key, the local variable key for this particular ICE process. It sets it to the result of that test and set. And so we get this key, and we then come down and we set waiting equals to false because it's no longer waiting. And so that waiting variable or position in the array for the ICE process talks about the status of the process. Is it waiting to enter? It's currently held within this acquisition or acquire for the lock. So that's the lock acquisition here. Or is it in the critical section? So it's not waiting, so it sets its waiting position I in this waiting array to false, and then it enters the critical section. So here is the critical section. And so now the first process or thread is done with the critical section. So what does it do? It's going to set J to be the next process from the ICE process itself. And it's going to do it in a ring-like fashion. So if you are the fifth process, I, then the next turn is going to be the sixth process. So it does that increment, and then it waits or checks to see which next process is waiting or not waiting. And so it says, okay, well, if it's not myself and the other process J that I selected is not waiting, well, I keep incrementing. And so what this part is doing, it's saying select a process, PJ, the Jth process, that is not waiting, that is waiting. And so here, as long as you're not waiting the Jth process, well, you don't need access to the critical section. And so it keeps going until it encounters a PJ who's waiting in to access this critical section in this lock or this entry code block. All right, so once you select the first process PJ that is currently waiting to enter the critical section, you check to see if it's yourself. If it is yourself, you set the lock to false. If it's not yourself, then you set that process waiting to false. And what happens here? Well, if you set that process to false, well, eventually that waiting is going to drop out and it's going to do the test and set. And if you were yourself, you then set the lock to false and it's going to drop out. And then the next process, PJ, its key is true and it's no longer going to be waiting. Waiting J is false. So it's going to drop through and not execute this while loop and enter the critical section next. And so this bounded wait with mutual exclusion is afforded by this atomic test and set. And what that does is it only allows one process at a time to set this lock variable from its initial status of 0 to the new status of 1. And then we can then set this, or false, to this new status of true. And then we can, in the process, set it back to false again, or give the next process a turn to go past this lock barrier into the execution of the critical section. All right, so let's take a look at Mutex Locks. We talked about this test and set to implement bounded wait and mutual exclusion. Now, these previous solutions are pretty complicated, and they're not generally available to you, the programmer, and operating system builders gave tools to make this solution to the critical section a lot easier. And the simplest one is a so-called mutex. And mutex stands for mutual exclusion. And so a mutex lock protects a critical section through two applications: the acquire for the lock and then the release for the lock. So this is the acquire is the lock and the release is the unlock. And so there's an associated Boolean variable that indicates the availability. Is the lock available? True, or is it not? False. And so calls to acquire and release, those two functions must be atomic so that you have a consistent state of this underlying Boolean lock variable. And so this is usually implemented as an atomic instruction supported by the hardware, going back to that lock prefix for the inline assembly that I mentioned at the beginning of this module. But the solution requires busy wait, meaning that you have this while loop that you sit inside of. And so you're still executing when you have this spin lock, as it's called. But it is effective, can be effective, in arbitrating the serialized access to the critical section. Okay, so here we have imagining that we are setting the acquisition and the release atomically. And so the acquire function, as long as it's not available, you busy wait. And then once it is available, right, you set it to false. Okay, so then the release then says the lock is available, you set it to true. So if available starts out as true, not available, you're not busy waiting, you come through, and then you do this acquisition, and you set it to false. It's no longer available. And if it's no longer available, the next thread that comes in and tries to do the acquire, it's going to sit in this busy wait, and it's not going to exit the acquire function, and therefore not able to execute into the critical section. And so here we have the acquisition, there's our acquire, we have the release, there's a release, and we have the remainder section. And so in doing so, if we have an atomic acquire and atomic release, we can implement this mutex-like behavior using atomic versions of acquire and release. Okay, so let's take a look at this other version. This other version is so-called Semaphore. And so synchronization with a Semaphore is much more sophisticated than a mutex. And for a process, if it wants to synchronize its activities loosely with another process, and I'll explain what I mean by that, Semaphore allows you to implement that. And so a semaphore is associated not with a Boolean, it's associated with an integer variable. And as an integer, it's going to represent a count of the number of threads or processes that are allowed to access the critical section. And so this serialized access is a special case of a semaphore, in that a semaphore with a count of 1 allows only one thread to access the critical section. And so the semaphore, and therefore the critical section made available to threads that call the acquisition function, can only be accessed using two atomic operations. And so the semaphore, and therefore the underlying critical section, can be accessed using two atomic operations. One is called the wait function, and this wait function is like the lock function that we talked about with mutex, and the signal is like the unlock function that we talked about with mutex. And the wait and the signal are both atomic. And so in their implementation, they'll use the atomic instructions on the underlying CPU, if not offered through C11 through an available existing API. And so in the early days or earlier days in operating systems, the wait was called the P function and the signal was called the V function. Now, at Free University in the Netherlands, a lot of this stuff was developed, and so they used the Dutch words for proberen, which is Dutch for to test, and verhogen, which is the word to increment or to increase. And so originally they were called the P function and the V function for the Dutch probe and for Hogan. Okay, and so let's take a look at what the wait function does. Now, the wait function, it tests the P function, probe for the status of the semaphore, which is associated with the semaphore variable, to see if it's less than or equal to 0. Now, if it's less than or equal to 0, that means you are not allowed access. And so initially, if that S is equal to 1, it means only a single thread can access the critical section. So the semantics of the wait function, the P function, is you start out in a tight loop. You're going to busy wait if that semaphore variable, the integer, is less than or equal to 1. And then if it's not less than or equal to 1, you come down here, and then you're going to decrement it. So if it starts out as 1 in the outset, only one thread can access critical section. You decrement, it is now 0. And the second thread that comes along executes this wait function, this lock or probe error. It's going to busy wait because at that juncture, that single unit of access has already been granted, and the first thread that called wait decremented it as part of the wait semantics. Now, this wait is going to be atomic. So this function will execute in its entirety, and any thread or process that calls it is going to be allowed to exit or complete this execution. All right. Likewise, the signal, or the Verhogen, that is going to increment because a V function increase, and that's the unlock or the exit section for this semaphore. And so what does it do? It increments. So it's saying, okay, well, I used up 1 unit of access, so S goes from 1 to 0, and now when I'm done as a thread with use of critical section, I increment it, so then S goes back to 1. Okay, now the interesting part is that if S starts out as 2, that means 2 threads can call wait and enter the critical section, and then they both restore or return their lock or their key, if you will. They return that unit of access to the critical section back to that variable S. Okay, so this is the wait and the signal, or the probe and Verhogen. And so sometimes semaphores are called counting semaphores, and the integer value can range over an unrestricted number of values. Now, certainly, if you have a number, an integer that's more than the number of threads on your machine, that kind of defeats the purpose. But nonetheless, it's counting semaphore because it uses an integer as the key variable used to define how many units of access to the critical section are going to be granted by this particular lock or wait section. And so a binary semaphore is one where the integer only ranges between 0 and 1. And this binary semaphore, if your integer S is set to 1 at the outset, it only grants a single unit of access to the critical section, and it behaves just like a mutex. And so beyond just what a mutex does locking and unlocking. A semaphore can solve more sophisticated synchronization problems. And so let's consider 2 processes, P1 and P2, that requires some code to be executed called S1 to occur before S2. Now, of course, if these processes are executing concurrently, we don't know what order these are going to occur. So the code for process P1 is here. The code for process P2 is down below. So we define a signal semaphore called sync, or synchronization, and it's initialized to 0. And so the first thing P1 is going to do, it's going to call its code S1, and then it's going to signal this sync semaphore. Signal, we said, is the V function for Hogan, and that's to increase or increment. So at that juncture, S is equal to 0. P1 gets to run its code S1. It occurs first. And P2 at the same time, concurrently, S is equal to 0. And what does it do? It calls the probe error, the wait. Now, because S is initialized to 0, P2 has to wait here. It does not, in its execution, go past this P function, this wait. And so P2 then waits for this S variable to sync variable to equal 1. And so when the signal is called after P1 executes S1, that happens first. And then it signals that semaphore variable. It increments from 0 to 1. And now as 1, P2's wait unblocks, and it can now proceed in this execution and execute S2. And so in this case, it doesn't matter what the execution of P1 and P2 is. You can guarantee using the semaphore that P1's S1 code and P2's S2 code are going to proceed in the order S1 followed by S2, regardless of the order in which P2 and P1 are executed on the CPU. And so you can implement a counting semaphore as a binary semaphore. It has mutex-like behavior, but the way it works, it can give you much more sophisticated synchronization semantics between a number of processes. And so for the implementation of a semaphore, you have to guarantee that no two processes can execute the wait and the signal on the same semaphore at the same time. And so this is where the atomic instructions become really, really important. So the implementation that I showed where it had a while loop, that becomes a critical section problem where the wait and the signal code are placed in the critical section. Now you can have busy waiting in the critical section, but this is not a very good practice. It's a lot easier to have your thread spend minimal amount of time in the actual critical sections, and therefore it's not good to have your busy wait as part of your critical section. And so a solution for this is to remove this idea of busy waiting, and that's what's done in practice. Each semaphore is then associated with a wait queue, just like how you have an I/O device associated with a wait queue. And then each entry into a waiting queue has two items in it. So you can have a data structure, a queue of data structures, C structs, user-defined type. It's going to have a value, it's an integer, and it's going to have a pointer to the next record in the list. So it's a singly linked list. It's a queue. All right. And so you're going to have two different operations. You're going to have a block, and this is going to place the process invoking this block operation on an appropriate waiting queue. And so the semaphore, by associating a waiting queue with the semaphore variable, you're going to put a process that would have executed in the while loop in a spin lock. It's going to be now put on a wait queue. And then you're going to have the exit section associated with the semaphore implement a wake up operation. And so what this wake up operation is going to do is going to remove one process in the waiting queue and place it in the ready queue. So now it's able to execute in the critical section. And so we have a C struct. You're going to have your value, your integer, and then you're going to have a pointer implementing your list. This is going to be your queue. And this is what a semaphore is, where the value is the semaphore value, and that list is the waiting queue associated with that waiting set of processes that are now blocked until they can get access to the lock and execute, therefore, in the critical section. And so here's some pseudocode for this operation. So this is the wait, the P function, and a new version of the V function for Hogan. And so what does the wait do? It takes the value, decrements it. So we still have the same semantics of the wait is using up one unit of access to the critical section. And if the value of S is now negative, right, non-zero, what do? You add that process to the list, and then you block. And so now you add it to the list and you block, that process is physically no longer executing. It's waiting. It's in the wait state on the wait queue associated with the semaphore. So then, let's say if S is equal to as non-zero, right? And you decrement, you go from S is equal to 1, you decrement it as a thread coming in. You have 1 unit of access to the critical section. So you decrement it, it goes to 0. Is it less than 0? No. And so you skip past this, and now you enter the critical section. And then once you are done, subsequent threads that come in, they block, they're added to the wait list, and then the thread that made it through to execute in the critical section, it does the V function, the signal, and it increments S. So now S is no longer 0 after you decremented, went from S, goes from 1 to 0. S is now equal to 1, and then you remove a process from the list, that wait queue, and then you wake that process up, and then you exit the signal, and you're done with critical section, now at the remainder section that follows below. Okay, and so the thread that exits the critical section and calls the signal, it wakes up some thread that is currently blocked on this wait queue associated with the semaphore structure. Okay, so one of the things that can happen is deadlock. If you don't use your semaphores correctly, a deadlock occurs when two or more processes are waiting indefinitely for an event that can only be caused by one of these waiting processes to proceed. So they're in this deadlock situation. I'm waiting for something from you. At the same time, you're waiting for something from me, and we don't make any progress. So suppose we have two semaphores, and they're both initialized to 1, S and Q. And so that means S is going to admit 1 unit of access to critical section, and Q is going to admit 1 unit of access to critical section. So you have two processes, P0 and P1, and P0 does a wait on S. So if you wait S, S is now starts out as 1, and S is equal to 0 at that point, and then P0 continues to execute. So then P1, it does a wait on Q. So Q is equal to 1, does a wait on Q, and now Q is equal to 0, and P1 starts executing down here. So then P0 does a wait on Q. Well, Q is equal to 0, so what happens? P0 is going to block. It's going to wait here, and it's going to be put on the wait queue associated with the semaphore Q. All right, so P1 then executes and does a wait S. Oh, S is 0 at that point. It's going to block, and it's not going to execute. It's going to be put on the wait queue associated with semaphore S. So P0 is waiting for someone to signal semaphore S, and it's blocked. And P1 is blocked, waiting for someone to signal semaphore S. And P0 is blocked, waiting for someone to signal semaphore Q. And so this is a deadlock because at this point, both PQ and P1 are in their respective wait queues. P0 is on the wait queue for semaphore Q. P1's on the wait queue for semaphore S. Now, somebody needs to come along and signal Q in order for P0 to wake up and continue execution, and somebody has to come along and signal semaphore S for P1 to wake up, but they're both waiting for one another, and therefore we are deadlocked. No progress happens. Okay, and so another thing that can happen is starvation. You can have blocking indefinitely. A process may never be removed from a semaphore queue in which it's suspended if some other things that are higher priority come along and grab the semaphore. Priority inversion is another thing that can happen. You have a scheduling problem when a lower priority process holds a lock that's needed by a higher priority process. Now, in that case, you need a special protocol to resolve that. And so that lower priority process, it can end up blocking a higher priority process if the higher priority process does not make progress. And so with that, you can have that lower priority process through a priority inheritance protocol temporarily assume higher priority and therefore finish its execution and release the lock in a much more timely fashion. Okay. And so there are some problems that can happen with the incorrect uses of semaphores, right? You have to make sure that programmatically you're using them correctly in order for your programs to work. And so suppose you have a mutex and you signal that mutex, and so your signal, okay, that wants to do an increment, and then you do a wait on that mutex. Well, one of the problems here, remember, that signal is going to increment. That's the V function. The wait is going to decrement. And so in that case, you're not blocking at all in this region between the two, right? You're incrementing and then you're decrementing. Wait a minute, that's kind of weird. Not really waiting at all. And so you're not blocking at all, not controlling access. And then what if you did a wait on a mutex and then another wait? Well, the wait, okay, that decrements, but another wait, you never unlock it. You're just now blocked and nothing happens. You can also emit your wait or your signal or both. And so you have to start out, when you enter, you do a wait. That's your P function. You perform your critical section, and then you do the signal. And you have to do it in the correct order, right? And that's also if you're doing it to synchronize between two different processes. You have to make sure that you're using them correctly. Otherwise, deadlock and starvation are possible. So let's lastly look at this last concept. We're going to look at monitors. Now, monitors are a high-level construct, and it provides very effective access to synchronization between processes or threads. Now, it's an abstract data type, and it has a number of internal variables, And these variables can only be accessed by special codes, special functions, certain procedures. And so you can't write an arbitrary function to access these internal variables. You can only use the functions that are associated with the monitor itself. And only one process at a time can be active in the monitor. So that's a given. So it provides for serialized access, but you can have a lot of sophisticated coordination between the processes that are executing the critical section of these critical variables within this monitor. And so it's not powerful enough to model some synchronization schemes. And so this monitor gives you a very sophisticated way of doing synchronization. So you define your monitor, it has a name, and then you have some shared variables declared inside of it, and then you have a number of procedures, and these procedures can all interact with, modify, read, and so forth, all of these shared variables. You also have some initialization code. You might want to set things up when a thread or process that is executing in the critical section associated with these critical variables that it needs to initialize before it calls these routines. And so the functions that can be performed are only these procedures defined and associated with the monitor, and these functions operate on these shared variables. Okay, and so here we have our shared data for this monitor, and this figure is in the book. We have our initialization code, and then we have our different functional blocks of instructions, our functions, and these functions operate on the shared data. And so we have something called an entry queue, and we said at the outset that only one process or thread at a time can execute in the monitor. So only one process in this queue can now call one of these functions. You could call the first one, and the second one, the third one, or what have you. But once a process or thread enters the monitor, you can exercise these methods or these functions, and these functions will operate on the shared data. And so you can call a number of these functions, these operations, and then you leave the monitor. And once you leave the monitor, it's now another thread or process's turn to execute functions within shared data. So the nice thing about this is that these functions give you a well-defined set of operations that you can perform on the shared data. You can't just arbitrarily interact with the shared data directly, right? You have a nice orderly way to define the set of operations that you're allowed to execute on the shared data when you call these procedures associated with the monitor. Okay, and so you also have in the monitor these synchronization primitives. These are called condition variables. Now, certainly in languages like Java, you can have a condition variable to synchronize processes of threads without necessarily being part of the monitor. But nonetheless, these condition variables have two different operations, and they implement semaphore-like behavior. And so two operations allowed on a condition variable are the wait, just like in a semaphore. A process invokes the operation wait is suspended until somebody comes along and does a signal. And likewise, the signal resumes one of the processes that invoked the wait. And so the wait acts like this block for the semaphore, and the signal acts like that wake up on the semaphore. And so if no wait is called on the variable, then it has no effect on the variable. And so a condition variable is almost like a semaphore in its behavior, but it's disassociated from the semaphore. It's associated with a variable. Okay. And so you can have a sophisticated set of synchronization mechanisms and locking mechanisms if you have a monitor that includes condition variables inside. So you have your monitor, your initialization code down below. You have your shared data. So these are almost like instance variables, if you will. And these shared data are only operated on by your procedures. The first one, the second one, up to the nth one. These procedures define a library of operations that can be performed on the shared data. And only one thread or process at a time on this entry queue is allowed to execute within this monitor, therefore call these procedures defined on the monitor that manipulate the shared data. And so you also have queues associated with these condition variables. And so each condition variable, if we have condition variable X and Y, they're associated with queues. Now, these can give you these very sophisticated synchronization mechanisms. Maybe you want one process to do one thing and another process to pick up the result of what the other process did, resume, do something else. Well, this is what you can accomplish with the wait queues associated with these condition variables. You can have sophisticated synchronization, like we explained when we had one process run one block of code that had to happen before another block of code occurred. So imagine one block of code loaded an image and the other block of code did some image processing on that. So you can do this very sophisticated handoff between processes, all within a monitor with a critical section that is your shared data that has well-defined procedures that you can perform in a library of procedures, P1 through P procedure N, on each one of these shared variables. Okay, and so if process P invokes x.signal and process Q is suspended by calling x.wait, what should happen next? Well, ideally, the signal should cause the other process that's waiting on x.wait to wake up, be selected off of its wait queue associated with condition variable x, and then resume. But both Q and P can't execute in parallel. And why is that? Because both P and Q, if they're running in a monitor, well, we have process P, we have process Q. Now, if process P is running in the monitor and it uses a condition variable, and process Q is running in the monitor, they can't both execute in the monitor because only one process or thread at a time can execute these procedures in the monitor. So if P is associated with a condition variable and it invokes signal to try to wake up Q that's suspended, so Q did a wait on condition variable X, so process Q called X.wait, and now it is suspended. It's on a wait queue, and then process P comes along and it calls x.signal. Well, if P called x.signal in the monitor, they can't both be executing. So a number of things can happen because both P and Q cannot execute in parallel. If Q is resumed, then P has to wait. So if P signals on X, P is going to have to wait if Q is supposed to wake up and continue its execution. Well, there are a bunch of things or approaches that are taken. One's called signal and wait. So if P waits until Q, either Q leaves the monitor or Q waits for a different condition, then P can execute again. So P is called signal and wait. Another is called signal and continue. So P signals Q, who is blocked on the queue, wait queue, for condition variable X, and then P leaves the monitor or waits for another condition. All of a sudden, Q can run. So the signal and continue says P does the signal and it continues until it exits the monitor or it reaches a natural pause point where it blocks because it called wait on another condition variable. Now, both of these approaches have benefits and drawbacks, and it's really up to the language implementer of these constructs, these monitors with condition variables, to decide what the behavior is. Now, other languages implement bindings for this. Mesa C# has these condition variables as well as monitors. Java does as well, and perhaps we'll get a chance to tinker with this in a future project assignment. So that's a hint to make sure you understand monitors. All right, and so what do you do when you resume a process within a monitor? Let's say you have several processes that are queued on a condition variable. So we have process P1, process P2, some number of processes Pk, and each one of them called x.wait. So associated with condition variable x, we have the wait queue, and that wait queue has process P1, this process P2, all the way up to and including process Pk. Now, of course, if some other process comes along, let's say process Pn comes along and it calls x.signal. If it calls x.signal, now we said the signal is going to wake up a process that's on the queue. So which process on this wait queue do you wake up? Well, oftentimes first come, first serve is not adequate. And so if it's a queue, first come, first serve says whichever one was queued first, let's say P1 was at the head of the queue, then it's going to be selected for execution, but that might not be the semantics or behavior that you want. And so there's a conditional wait construct that some language implementations of condition variables implement, where that wait has a parameter, and that parameter is a priority number. And so when you create your processes or threads, you give them priorities. So maybe this is priority 1, this is priority 2, this is priority 3, and so forth. And when you say wait, give it a priority number, and the process with the lowest number, i.e. the highest priority, is the one that's selected. So you're saying, I want to wait, but when I wait, I'm going to associate myself with a priority 1, priority 2, priority 3, that says when someone comes along and signals, who's going to be selected first for waking up and continuing the execution when they're woken up off of this wait queue and are allowed to execute either when the calling process PN exits the monitor or it reaches a point where maybe it blocks wy.wait blocks for a different condition variable. Okay. And so this resuming has to be done carefully. And one deliberate way of deciding is using these priorities, i.e. this conditional wait construct, associating priorities with the process on the inbound side when you call the wait on the condition variable. All right, so with that, that's all I had. And we are done with our module on synchronization. Again, please make sure that you are staying on top of the reading. And Project 2 is due tomorrow, Wednesday, at the usual 1 second before midnight. Please make sure you are following the instructions and you make sure you are not losing points. Don't lose points for careless errors. Okay, so with that, as usual, please stay healthy, stay safe, and I'll see you all on Thursday.